Hi everybody! Welcome back to Chem 163. Let me just wind this down. There we go. Oh no, someone is here. Say hi. There we go, very good. Maya says hello. We're going to finish chapter 16 today, because there's not really that much left. This is the last really important section. The last three sections are things like, oh, this is what an actual battery looks like, this is what corrosion is, etc. And we'll briefly look at those. There's a little bit of stuff in electrolysis that involves math that we're just not going to do because we're out of time, and I do want to actually get to chapter 17 to just introduce it because there's a lab about it on Friday. So that you aren't looking at the lab for lab number 7 and going like, what the heck? I'm so confused. So, the thermodynamics part of electrochemistry is actually surprisingly easy because we already have 2 of the terms that we know for thermodynamics regarding reactions being spontaneous. So we already know delta G and K. And all we do is add E cell into there. So we know that if you have delta G and is a negative number, or K is a number greater than 1, such a reaction will proceed in the forward direction. Well, we talked about doing an electrochemical cell and calculating E cell for that. And if you get a positive number, that reaction is spontaneous too. So using all of those things, we could just put these 3 terms together and make a bunch of formulas that relate them all. If you want the reaction to be non-spontaneous, you just flip them or invert them. So delta G would be a positive number for a non-spontaneous reaction. E cell would be negative, and then K would be less than 1. On their own, that's kind of weird. Like, why can't we unify these? We just didn't. Thanks, physics. Thanks, chemists. You know, what can you do? So, obviously, some relationship must exist, and here it is. I said, where is my relationship? There's I'm thinking of this chart. There it is. It's 10 slides away. So here is the relationship between delta G, E, and K. Now, I personally I don't ever use this formula down here. If I'm calculating K, what I end up doing is I do this, and then I figure out what this is. But on a quiz or an exam, hint, like your quiz this week, if you use the equation down there at the bottom, that's totally fine. Oh no, hold on. My cats are fighting. Hey! I guess I didn't pay attention to Maya, so she ran to go beat up Kresnik or something. If I hear them again, I'll have to stop and go get them, but we're going to go over those formulas in a second. These slides are just going to prove how you get that relationship here. So, to relate delta G to E cell, we know that E cell is in volts, right? And volts are joules per coulomb. Well, we can express joules as work and coulombs as charge. And if I rearrange this equation, then I would get the work for the done by the reaction would be equal to the charge times the voltage. What we're going to do is we're going to replace this term right here with a number. We're going to count all the charges in moles, and then we're going to multiply that by the amount of charge per mole, which is this constant that you saw on the lab last week, and I was mentioning it. You've probably seen it in the lab this week. This is known as Faraday's constant. And I believe Faraday's constant is on the next slide here. Yeah, there we go. Now, the reason that we use Faraday's constant times n is because we can count the number of moles of electrons very easily. So if we had a balanced equation, say something like this. So let's go over here real quick. And we did okay, well, I have aluminum and copper becomes this, for instance. Well, your reduction would be this. Well, not that, but... And your oxidation would be that. And then we would balance the equation, so I'd go, okay, well, this is 3, 6, 3. And this is 2, 2, 6. When we cancel out these electrons, or you know what, we'll just do this. This tells us the number of moles of electrons that move for my balanced reaction, whatever the balanced reaction is. So for this reaction, 2 aluminum plus 3 copper 2 makes 2 aluminum 3 plus 3 copper, and would be 6. So if I was studying this reaction and trying to figure out like what delta G was for this reaction, I would have to figure out the number of electrons that are moved from the reduction, or to the reduction side from the oxidation side. And in order to get that, you have to balance the equation. So this is another reason why we don't scale E. Excuse me. This is another reason why we don't scale E when we multiply an equation. So remember that when we look up the numbers in Appendix L for these reactions for E cell, for each half reaction, we just copy the numbers, right? We do the scaling in the formula when we have N. We multiply N times some constant times E cell. And that's going to look like that. So this expression relates to the amount of work that you can do in a system. And then since delta G is just how much work can a process give you, you just swap out W for delta G. So this reaction will tell you the maximum amount of work an electrochemical cell can do. So that's useful because now we can relate electrochemical cells to anything from thermodynamics. So this can then become this reaction, or not reaction, this equation, and so on. There's other equations out there. I can't think of them right now. All right. So let's show a reaction. So here I have this reaction. I have some numbers from Appendix L. What we're going to do is we're going to figure out delta G for this reaction and determine if the reaction is spontaneous or not. Now, you don't need delta G to figure out if it's spontaneous. You could just use E cell. So by manipulating these two things, I should be able to predict whether the reaction is spontaneous or not. But then we'll calculate E cell for it. So let's go over here and capture nothing. That's always important. All right, so now I got to write out my half reactions so I know which one's happening at the cathode. So I got my reduction and oxidation. So according to this reaction, which element is being reduced? Well, it looks like iodine is gaining electrons because I've got I2 and I end with I minus. Specifically, I end with 2 I minus, so I'm going to give this 2 electrons. And then, which one's being oxidized? Well, which one's losing electrons? Well, if I have Br minus goes to Br2, specifically 2 Br minus, I have to remove 2 electrons to do that. And then when my electrons cancel out, my redox reaction is just this. Maya, stop. She's sitting in the hallway. Her head is peeking around the door, looking at me like, oh, I'm so bored. Please pet me. I'm just like, no. So there's our reaction. I'm going to write this over here. Just to remind me that, hey, when I canceled out my electrons, I got 2. And then I need to figure out what E cell is. Well, remember that E cell is just cathode minus anode. And so reduction occurs at the cathode, and oxidation occurs at the anode. So we'll go look up these voltages. So E for iodine, according to my little chart there, was 0.54. And E for bromine was 1.09. And so this would be, so the cathode is 0.54 minus 1.09. Well, I have a calculator on screen. I was reaching for my calculator on my desk there. Minus 1.09. So we get a negative number. And so we would immediately conclude, well, this can't be spontaneous. And then now we can figure out delta G for the reaction, because we know delta G for this reaction is equal to minus N Fe cell. N is 2 moles of electrons. Faraday's constant was 96485 coulombs per mole of electrons. What is that sound that they're making? Oh my goodness. I have to go yell at my cats. And then finally, E cell is whatever number we calculated. And then a volt is a joule per coulomb. So my coulombs will cancel out. And because it's delta G, I should get something in energy terms, right? Which would be joules. So negative 0.55, we already have that in there, times negative 2 times 96485. There we go. So I get 106,133 joules. I only get 2 sig figs, so this is going to be 110,000 joules, or 110 kilojoules. So this process would actually require 110 kilojoules for me to input into the system to get iodine to reduce bromine. Or I'm sorry, iodine to oxidize bromine. Iodine is getting reduced. Now, the next question that I have here is, well, based on our information that we are aware of, and also what we've learned in Chem 161 and 162, why would iodine not be able to oxidize bromide? Well, I got I2 here. Why would I2 not be able to take electrons from Br minus? I hope you remember what your information is about electronegativity and the trends of it, because, well, you know, the final exam is cumulative over not just 163, but 161 and 162. So, if you remember a term called electronegativity, bromine is less electronegative, or I'm sorry, bromine is more electronegative than iodine. So, an element that's more electronegative will keep its electrons relative to an element that's less electronegative. So, the opposite process would occur, but bromine is going to keep its electrons, and iodine can't pull them off. Yeah, it is electronegativity. Very good. Oh, I gotta click over here. There we go. Alright, so I'm going to give you this reaction. This is the first reaction I do in 140. I show this reaction, and we get to watch sodium explode. So, We're going to reduce water with sodium metal. And in doing that, you get hydroxide and hydrogen gas. So we have this reaction down here, which is the She. And what I want you to do is tell me, is this reaction spontaneous? You know the answer is yes. But just in case you were trying to find H plus and 2H and 2 electrons here, just as a hint, I could write H2O as that. And then if I put the other stuff on the other side here, and I just kind of carry it down, then these would go away. And what's left over is the She. So what we are actually doing is producing hydrogen from H+. It's just that the H+ is hidden in water right now. So using that information, I'll leave that on the screen while I go check on cats. I want you to calculate what E cell is for this reaction. And then from that, calculate delta G. And tell me, is the reaction spontaneous or not? I'll give you like 4 or 5 minutes. So I'll check in with you in just a bit. One more minute, we'll go over the answer. Oh my goodness, my cats today. I don't understand. Now they're opening cupboards and stuff. Alright, where are we? We're over here. I want everything on here. So let's do that. I'm going to erase this real quick. And we'll erase that. Okay. So we'll write down our reduction and our oxidation. The oxidation part's pretty easy. We're going to just do that one first. We're going to have to multiply this by 2, but we'll get to that in a second. And again, the reduction part is a little bit strange. We got it written like this. Now, you can do the way that I showed you, and then over the break I was thinking, well, why don't we just balance it like we normally do in acidic solution? Since we want some acids left over, right? And so, I have 2 hydrogen on the left side. I'm sitting here looking at this. Where's my 2 going to come from? I'll just do this for now. So I got my O's balanced out. I have 4 H's. Oh, everything's balanced, isn't it? Well, what we'll do is we'll just do this. And then this is water. And then this is water. There you go. There's the she, right? So basically what we had before, get it basically? Boom. Is that we had balanced the she in basic solution. This is the she in acidic solution. And then I'm going to do this. I'm going to put 2's everywhere so that my electrons can cancel out. So we got that. And then our reaction looks like this. So we got 2 sodium and 2 H+. Makes 2 sodium plus and H2. So that's our net ionic equation. If we balance that in basic solution, which makes more sense based on what we observe in the reaction, because we create hydroxide, then we could add OHs over here. So this is water. And now it's the reaction that's shown above. So we'll scroll down here. So we need E cell is cathode minus anode. Well, the cathode was just the She up here, so that's just going to be 0. And then whatever the anode is flipped around. So negative 2.71 volts becomes positive 2.71 volts. So this reaction is spontaneous. And we knew that because when you drop sodium metal into water, it explodes. And then we could just do delta G equals NFE. Well, minus NFE, sorry. And we said that N was 2. F is 96485 coulombs per mole of electrons. And then our E cell here was 2.71 joules per coulomb. So let's punch all that in the calculator here. So we got negative 2 times 96485 times 2.71. And I get 3 sig figs, so 523,000 joules. Or negative 523 kilojoules. Either one of those is fine. All right. Now, let's suppose that you wanted to find the equilibrium constant for this. Well, we know that delta G equals minus RT ln K, right? So, could you solve for K? Of course you could. If I do this, and then if I undo natural log, that would be this. And so if I wanted to figure out what the equilibrium constant was for this, e to the minus delta G, which is 523,000 joules, divided by R, which is the ideal gas constant. I'm working in joules here, so I want the 8.314 version. If you aren't doing liter atmospheres, don't do 0.08 whatever. And then we're going to multiply by temperature. Oh, we have to pick a temperature. So let's do at 25 degrees Celsius. Just to make this work. Where does this moles go? Well, we could just say that this is per mole, and then they go away. Is it per mole? I might have to think about that. What's per mole of H2 created? It's fine. Anyway, the point is that when we do this, you're going to get this really, really, really small number. So E is this number, which we'll just round to 3 sig figs. So let's do that real quick. 523,000 over 8.314 times 298. So there's my exponent. We're going to do e to that number. Do I have this in my calculator? I do. So e to the negative 211 or something like that. Yeah, there you go. So there's how small the equilibrium constant is for this reaction. Oh, you know what I forgot to do? I forgot to do this. So I should get a really big number, actually. And that makes sense, actually, because delta G was negative. Okay, so e to the 211. There we go. That checks out. Okay. So because our reaction was so... Our delta G was so negative, our K must be extremely big. Not extremely small. I was looking at this number being negative and going like, oh, I'm going to get a super tiny number. Not realizing I lost this minus sign here. So this is what we're going to be doing in a little bit. So you can use this formula, or you could use the other formula that we're going to introduce here in a second, which is going to incorporate n into it. And so since you have n available, that might also be useful to you. So there's our equilibrium constant. What we're going to do here to get the other relationship to go directly from E to K is I'm going to just set this equal to that. And then I'll have, well, minus n of E cell equals minus RTL and K. Well, I can get rid of the minuses. I can divide both sides by NF, and I can get this. Now, some people don't like working with all of these constants in here, and so what they do is they actually replace these constants with these values. So here's R. We're going to assume that T is at 298.15 Kelvin. We know what F is. And there's actually a relationship between natural log of K and log base 10 of K. And really what all of this does is all these constants come together, and you get this 0.0592 over n thing. The caveat of this is that it switches log from natural log to log base 10. I don't know why they did this. Like, why are we suddenly invoking log base 10? When all along we've been doing, like, natural log of whatever. But, okay, this is what they did, so this is the formula that we have. So this version of the formula really just simplifies, but very, very, very important. This is only really helpful to you if T is 298. And if you're working with standard states, well, standard states, T is 25 degrees Celsius, right? So it is 298. But if you're not working at standard states, then you have to account for that when you're doing this reaction. So let's look at this reaction. And we're going to figure out the equilibrium constant K for it. And before we do that, I'm going to write down the formula because I never remember this number. The 0.0597? It's 2. Okay. So let me write that down real quick. I'm the kind of person that would just dump all of the numbers into the equation. So I would prefer to use all the variables, RT and F, L and K. Oops, that's as far as I want to go. So we'll go over here. All right, so we can do the same thing that we did before. We can just figure out what E is for this reaction. So let's do our reduction oxidation. So what's being reduced here? Well, it's the She again. So that's great. And then what's being oxidized? Well, it's copper. And what's that E? 0.34. So E is going to be cathode minus anode. We know that reduction occurs at the cathode, so that's going to be 0. And then oxidation occurs at the anode. That's not the number I want. So, oops, hold on. So we know our reaction is not spontaneous. And now we can go plug all of those numbers into this equation up here and get K. Well, I have to solve for K up here, so hold on. We're just going to paste this down here. So let's solve for K. So that means that I have N times E cell divided by 0.0592 would be log base 10 of K, and then 10 to this. And this number is actually in volts. I should be writing that. Equals K. So what was N for our reaction? I didn't actually write it down. Looks like it was 2. And then E cell was negative 0.34. I don't know why they don't include the units for moles of electrons here. This should cancel out with something that was wrapped up into this. Specifically the F part for Faraday's constant. So we're just going to get rid of it. These volts go away. And why am I being messaged? I hope it's not someone saying, hey, the stream is down. Oh, it's not. Okay. So let's do this calculation. So 2 times 0.34 divided by 0.0592. So that's my number in the 10. I'm going to do 10 to the x of that. Boop. And I get this ginormous number, which looks like 3 times 10 to the 3, 6, 9, 11. That's what I got for K. Wait a second, hold on. This should be a tiny number because this is... Oh, I know what happened. Hold on. Undo, undo, undo. I didn't type in a minus sign. That's what happened. So 2 times 0.34 negative. So guess what I forgot? I forgot this. Divided by 0.0592. Yeah, now I should get a tiny number. Yeah, that makes more sense. Okay. Remember, you can always check your work when you're doing this, because if you look at your E up here and you're like, oh, it's negative, well, then my K needs to be less than 1, right? And so when I got down here and I got a positive K, I was like, well, wait a second. I screwed up somewhere. And most of the time, it's going to be these minus signs. So I wish I could say I was doing this with this in mind. It was like, oops, lost the minus sign. What happened? Got a weird K. But no, I'm genuinely just making mistakes because I can't read my own handwriting. So, but when you do enough of these problems and you understand the relationships, you can at least go back and check and be like, oh, okay, yeah, this doesn't make sense based on the number that I got before. All right. That is basically everything that I care about in chapter 16. So I'm going to have you do one more of these. So when you tell me the equilibrium constant for this reaction, here's some more numbers from Appendix L. It's our favorite She electrode, and then we have the iron being reduced, iron 3 being reduced to iron. Tell me what the equilibrium constant is. You do need to calculate E cell for this. We'll check back in about 4 minutes, and then we'll go over the answer, and then it's probably break time. So, see you in a bit. All right, one more minute. We'll go over the answer. All right. So I'm going to go back over here, but the first thing I'm going to do is copy this formula. That's not how we copy. That's called crossing everything out. Okay, so we're going to copy that. The selected area is empty. Oh, well, you know what? We can just do this. That didn't do anything. Oh, Photoshop. Okay, so we've got that copied. We're going to delete everything, and then we're going to paste. That's just great. Nothing happened when I pasted. Where is my formula? It lives down there for some reason. Ugh. Computers. Okay. We need these voltages, and this needs to be right there. Okay, perfect. Thanks. All right, so what's reduced? Oh, it's the she again. Surprise, surprise. Gotta have 6 electrons for that. And then what am I oxidizing here? Oh, it's iron. Hooray. So that'll come in handy later. And then we can figure out, excuse me, the voltage. Cathode minus anode. And that's going to be 0 minus negative 0.036. So there's our voltage, which means that the K we get should be positive. It's not going to be ginormous, but it's going to be positive. And then we'll just get our favorite formula back, which should still be right here. Whoop, there you go. And then we'll just rearrange the expression again. So it's the same expression as we had before. So 10 to the n times E cell divided by 0.0592 equals K. So n was 6, and E cell was 0.036 divided by 0.0592. And what do we get when we do that? So 6 times 0.036 divided by 0.0592. 10 to that. 4,452. I'll take 2 sig figs here, so that would be 4,500. Something like that. All right. There you go. That's chapter 16, I think. When we come back, I'm going to very briefly go over the last, 50 slides in 10 minutes, just to touch on some points there. But we're going to take our break now. Oops, I need the timer. Timer. There we go. Boop. Oh, it didn't boop. Why didn't it boop? Live split, what are you doing? Live split doesn't want to work today for some reason. That's really weird and strange. Hold on. Why isn't this working? You know what we can do. We'll just open up. I have another way to deal with this. It's just, today is a day where everything breaks, I guess, so. Hold on. Nothing is working! Why won't you? You know what? I'll worry about it. I'll figure it out later. Here, we'll just go take a break. Oh my goodness, why did you just suddenly appear? I hate everything. Okay, well, now I have 17 copies of it open. Great. No, come back. I need you. I don't understand. Nothing makes sense anymore. Goodbye. There we go, we're back. Hopefully everything is working and my computer isn't, like, about to explode or something. Alright, on the screen here are the formulas that relate delta G to E cell and K. And really, these are the formulas you need to have available to do all the thermo calculations in this chapter that I care about. So, I'm not going to test you on the Nernst equation. I am going to talk about the Nernst equation real quick. So, if you were to try and calculate the voltage of a battery where you weren't at standard conditions, so remember standard conditions, excuse me, let us use this little circly guy for E cell, and all the solutions have to have a standard concentration of 1 molar. It's all going to be at 25 degrees Celsius, yada, yada, yada. You could pick any concentration you want to, but then what you are at is non-standard conditions, and you need to calculate Q for that. Now, the voltage does change between standard conditions and non-standard conditions. Like for this reaction, we have more reactants. So we would expect the reaction to go towards the products. So the voltage should be bigger. It turns out it is in this case. Since we used this expression way back when we were talking about the relationship between the reaction quotient and the equilibrium constant, we can do that again here. So I know that delta G equals N of E cell, so I'm going to just put that in both spots. I'm going to divide everything by NF. And when I do that, I get this nonsense again, which I can then turn into 0.0597 divided by N. 0.0592. I never remember the numbers. And then there you go. So this equation is called the Nernst equation. And what's relevant here, for your lab anyway, is that you can calculate the reaction quotient by writing out whatever equilibrium you're looking at and saying, okay, well, Q equals my equilibrium expression. And then you just change the numbers however you want to, and the reaction will change appropriately. So for your lab, that's going to look something like this. And there's a few slides on this at the end that we'll just talk about. So here's your concentration cell that you are doing in the laboratory, more or less. You were doing like 0.1 and 1, I think. So we'll just change this to a 1, and this is a 0.1. I don't know why my phone is buzzing at me here. I'm trying to ignore it. What's going to end up happening for a cell that is made of the same components but has different concentrations is that the electrons are going to move away from the solution that has a lower concentration at the anode. So here we've got a low concentration. My electrons are going to move away from that. And the reason that they're going to do that is because when electrons move away, I produce copper 2+. So this is my product. But I do that on the diluter side. And when I do that, this number increases. Over here, when I have electrons coming to the cathode, my copper 2+ in the solution already sticks to the electrode, receives electrons, and becomes copper solid. And so this number goes down. Or I should say this number right here. Whatever it ends up being. Eventually, the two sides will have the same concentration. And when that happens, the battery is dead. And so that's really all I care about for concentration cells. You're going to explore this idea a little bit more in that last section in the lab where I said, dilute the solution, what happens to your volume or your voltage? Then dilute the other solution and tell me what happens. And so you could see that this will play around with your Q if we... Oh, I gotta go over here. If I gotta erase all these layers. Hold on. So if we write out this expression here, is it plus or minus? I don't remember. Minus. That's what I thought. Okay. I just want to make sure. So if I have Q for this reaction B, this, initially for your experiment in the lab, so this is your lab experiment. Initially, this is what Q would be. And it would just be 0.1 divided by 1 equals 0.1. And so you could plug all this into the Nernst equation and figure out what the voltage is. Then what I tell you to do is I say, well, okay, we'll dilute this number. Okay, well, you dilute it. So this changes. What happens to the voltage? And you'll see that the voltage goes up. So you play with the calculations and see what's going on there in the lab. That's really all I care about for that. The rest of chapter 16 talks a little bit about batteries. So these are all concentration cell stuff. I'm going to cough just a second. Sorry, I don't think I muted in time there. The rest of this talks about batteries. There are different types of batteries that are available. So if you've ever wondered why you get a 1.5 volt battery, it's because these are the common reactions that occur. We have manganese 4 oxide reacting with ammonium, and then we have zinc being oxidized. And we get about 1.5 volts, which is the common battery that you see. Batteries that are alkaline contain base in them. There's our base right there, KOH. And then there's some diagrams in the text that show you what batteries look like on the inside. A lead acid battery is what's used in your car generally. Rechargeable batteries, fuel cells, etc. They don't talk about lithium-ion batteries because they're more complex than the scope of this book. But yeah, that's batteries. Corrosion is just unwanted reactions that occur. And then electrolysis is just the reverse process of doing electrochemical batteries. So we can make batteries run in reverse by applying a current. And there's a bunch of slides on this if you just want to look at it. One practical application of electrolysis is that you can plate out metals. For instance, if you want to plate out chromium metal on, say, exhaust pipes for your Harley, then what you would do is you would hook up the exhaust pipes, which are steel, I would presume, into a solution that contains chromium ions. You'd run a current through it, and it would plate out chromium metal on the surface of your thing. Then you pull it out and you wash it off, and then you put it on your Harley, and it's all nice and shiny. So that's an application that you can do there. We're not going to cover that. We're just going to go straight to the end. Hooray! There we go. Because I want to get through some of Chapter 17, just so that you've seen something for the lab tomorrow. Not tomorrow, I'm sorry, for Friday. Alright. Due to how quick the quarter is basically gone, Chapter 17 is probably going to be the last chapter. I can't see myself getting through all of Chapter 17. I'm going to have to cut out some stuff at the end here anyway. Which is fine, I guess, but we'll get through most of the important stuff. Chapter 17 is about kinetics. Kinetics is the study of how fast reactions go. Some reactions go really quickly. Other reactions go very, very, very slow. Depending on the type of reaction, we may or may not want this. So, for instance, an explosion is a very, very fast reaction. Lots of energy is released. And we can apply that for things where we need to input lots of energy. For example, moving stuff. I need to move all this stuff out of the way. Well, instead of picking it up, I can just blow it up. Other reactions are incredibly slow, and we want them to stay that way. So, for example, rusting and erosion are very slow processes. We don't want rust. Rust is bad. Rust is not as sturdy as the original product iron is. Generally speaking, it gets in the way. It requires energy to reverse. We don't like it. So our study of kinetics is to figure out ways to change these rates to mesh up with what exactly it is that we want. For rust, we'd want to slow it down even further if we could, or even eliminate it. For things like explosions, what types of reactants produce energy that goes faster relative to others? That would make for a better substrate for exploding stuff. So this is called kinetics. And what kinetics studies is the rate of the reaction. So how much reaction occurs per second. Now, in a solution, we're going to just look at molarity. We're going to say, okay, we use up this much molarity per second. So the way that this is going to be expressed is going to be in the following manner. We're going to look at the change in, I want to go to this screen here, in stuff over time. And so the way that we do this is the following. So rate would be equal to the change in whatever it is you're looking at over the change in time. For example, if I was looking at like the rate of speed that I was traveling, I would look at how far I have gone and divide that by how long it took me to do that. So if I went 50 meters in 10 seconds, I'm going 5 meters per second. Now, if we were in calculus, we would write something like this. I don't know how many people have taken calculus. We're going to use algebra, so we're actually going to be writing stuff like this, where delta will just be some fractional amount, but is not infinitesimally small. So this is for calculus, and if I accidentally write lowercase d, that's why I'm doing that. But the intent is that I do this. So what we're going to do is we're going to look at our reaction above. So for the reaction shown there, since H2 and I2 are reactants, they are used up. So I could say that the rate of the reaction would be equal to how fast I use up H2 over whatever time interval I'm looking at. I could also say it could be related to how fast I use up I2 over the same time interval. Because I would use up the same amount of H2 as I would I2 in that time period. So their rate should be the same. Now, HI is a product. And we're going to make that. So when I calculate the rate for this, I'd have a positive symbol. And that would be equal to delta H I. divided by delta T. But you probably noticed this 2 up here. What does this 2 mean? What the 2 means is that I'm going to make this twice as fast as I use up the other things, right? So I need to accommodate my rate expression for that. Since I want these numbers to equal something that I'm going to call rate, well, if this number is twice as big, I need to multiply it by this so that those cancel out, so that this equals the rate, which then equals these things. So in other words, if I have some generic reaction that looks like this, then I can express the rate of this reaction as whatever the change in A is times 1 divided by its coefficient. And I can do the same thing for B. And I can do the same thing for C, but C is a product, so I'm going to make it positive. Or D. Or so on. I didn't put a little plus inside in front of this. That's okay. Now, on its own, this context doesn't. There's not enough context here. This doesn't really make much sense, probably, to most students. Like, oh, okay, I'm writing this rate expression. What does this mean? Well, this right here is just going to be some number that we're going to calculate based on whatever I put into the reaction mixture. So let's do a few problems, and you'll see how this works. So first, we're going to derive the expressions that we just talked about. And then there's the reaction that there's the sample reaction that I just wrote. And what's important here is that all of these terms individually equal what we're going to define as the rate of the reaction. Now, the rate of the reaction will be some value for the entire expression, and then you can use that number to calculate how fast things are used up or produced. And so let's do that. So, well, let's not look at this graph just yet. Let's go straight to the example. All right, so I'm going to put hydrogen peroxide into a solution of HI. And when it reacts, it makes this reaction occur. So I have peroxide plus 3 iodides plus 2 H plus makes a triiodide into water. I want to know what the average rate of the reaction is over this 10-second interval. And the chemical monitor that I've used is I-. It started at this and it went to this. So let's figure out what the rate of the reaction is. So the rate of the reaction would be equal to whatever coefficient is in front of our sensor. So our sensor is I-, so that's going to look like this. Delta I- over delta T times, there's a 3 in front of it, so I go like this, 1 over 3. And then it's a reactant, so I have a minus in front. So I know, based on the problem, that the time interval was 10 seconds. And I also know what delta I minuses for this reaction. It would be final minus initial. That's how you do change of anything, right? Final minus initial. And so that would be 0.868 moles per liter minus 1 mole per liter. And I would get negative 0.132. So now, when I go over here to do this calculation, I learn that the rate is going to be equal to negative 1/3 times delta I, which was negative 0.132 moles per liter, divided by 10 seconds. And so that would be this times negative 1 divided by 3. And then all that divided by 10 seconds. This number that we got here is the rate of the reaction. Now, because we used a 10-second interval, it's going to be the average rate over that interval. If I used a different interval, I would get a different number. And we'll see why when I go back to the graph in a second here. So this number tells us that the reaction itself is going at 0.0044 moles per liter per second. Now, what does that mean for the individual reactants or products? Well, we're going to take that and equate it to the delta whatever it is for whichever product that we're using. So, for instance, if I wanted to figure out, well, what's the next question actually ask? Next question is asking me, what is the rate of change in H plus over the same interval? And so if we look at this for a reaction, I need the reaction on the screen, don't I? What you would say is something along the lines of, well, okay, if I used up some amount of I minus per second, I should use up slightly less H plus, right? Because there's a 2 in front of it as opposed to a 3. Well, how quickly did we use up I minus? It was negative 0.132 divided by 10. So we should get a number that's slightly less than that result. So let's see if we do. So the rate of this reaction will be equal to whatever change in delta H plus we observe over the time interval. And then because it's a reactant, it's negative. And there's a coefficient of 2 in front, so I'll do that. We already know what the rate is. The rate is this number right here. I know what the time interval is. That's still 10 seconds. So I just need to figure out what this is. So let's solve the equation for that. So the reaction will be the equation will be rearranged. So this will be 2 times the rate to take care of this 2 times delta T. And then I got to move the minus over. Will equal delta H plus. And so that's going to be negative 2 times whatever our number was from before. 0.0044 times our time interval. And that's going to be the change in delta H plus. over that interval. And it should be negative because it's a reactant, right? So I should be using this up. So let's see what we get. So I got this number times -2 divided by 10. Or not divided by 10. Oops, sorry. Let's undo that, and then we'll multiply it by 10. So in other words, I used up this much H plus over the same interval that I used up this much I minus. And we were able to determine that by using this rate right here. And that number checks out because it's like 2/3 of whatever our iodine number was, right? All right, so there's our answers for that. And then the next question is going to ask us, what would the rate of change for H2O2 and I3 minus be here? So what I want you to do is I want you to figure out what delta H2O2 is and what delta I3 minus is. Now, it's the exact same process. And hint, you should get the same number, but the sign will be flipped because one's a reactant and one's a product. So go ahead and try that. And we'll go over the answer in about 2 or 3 minutes. One more minute, we'll go over the answer. All right, so let's go over here. So for this one, I want to figure out what the change in H2O2 is over the change in time. Now, there's only one H2O2 per reactant, so I'm going to just do 1 over 1, which I don't have to write. So I'm going to just put the minus sign there. That's going to equal my rate. I can then solve for the change in peroxide by saying, okay, well, rate with a minus in front of it times delta T equals the change in peroxide. And so that would be negative 0.0044 moles per liter per second times 10 seconds. And so that would be for hydrogen peroxide. I would be using it up. I would have used up over 10 seconds that much. Now, how much triiodide would I have made? Well, since they're 1-to-1, I should make that much, right? Well, let's see if the reaction checks out. So rate would be equal to delta triiodide, delta T. It's a product, and there's only one, so I'd go plus 1 over 1, or just plus. So rate times delta T would equal delta triiodide, which would be 0.0044 molarity per second times 10 seconds or positive that number. So by using this rate number that we have right here, we can figure out how much stuff is consumed for products or reactants over some given time interval delta T. Now, if you've taken calculus before, you know that the change in product over change in time plotted on a graph would look something like this, and that the slope of that line would represent the rate. So for instance here, if we're still looking at this reaction here, so I've got H2 plus I2 makes HI, 2HI, sorry. I would use up H2 over a given unit of time. So I could say, okay, well, at this point right here, I'll make a tangent line. I could figure out what this value is as my delta y. I can figure out what this value is as my delta x. And then calculate the rate at that point. I could do the same thing for any point that I wanted to, and I could also do the same thing for HI. So in other words, the rate equals the slope of your concentration versus time. Oops, not change in concentration. Sorry, let me get rid of that. The change in concentration is what your delta, y delta x is. That's your slope. So if you need to do this graphically, you can find the slope of any part of your curve by either plotting a triangle like this or by doing calculus. You take the derivative of this expression and then just say, okay, well, what was the derivative at t equals 50 or whatever? Now, doing this process will give you what's known as the instantaneous rate. As you can see on the graph here, the instantaneous rate changes as the reaction goes on. At first, the rate is very fast because the slope is very sharp. So right here, my rate is much steeper than over here, and it's even steeper than over here. So the instantaneous rate is more precise, but you're going to have to calculate it more often. If you wanted to calculate the rate between two data points, that's simpler to do. So if I wanted to figure out this rate between these two data points, I would just make a triangle between them and say, okay, there you go. However, this is prone to error. Average data rate, or average rates are easier to calculate, but they are slightly more error prone. If you don't have all of your data plotted on a graph and you instead just have it in tabular form, figuring out average rates over given time intervals is much more straightforward. So for instance, let's suppose that I had H2, and I learned that after 10 seconds I had this much. I could say, okay, well, the difference between these two is what delta H2 would be for that interval. And since 10 seconds passed, I can use that to calculate the rate. Oops. So really, the choice of which rate you're going to calculate, average rate or instantaneous rate, is going to depend on whether you have a graph available and thus the equation of your curve. If you just have a bunch of data like this, it's easier to calculate the rate using the average rate. And yeah, you're going to have some error, but what can you do? At least you have some result, right? Note that the average rate does change over time, so all the rates change over time, always. The smaller your time interval, the more accurate your result will be. But since most reactions are slow to begin with, you don't really have to worry about whether you're using an interval of 10 seconds versus 100 or whatever. All right. We could calculate the rate of the reaction for anything or any interval that we wanted to. So, for instance, here, this is saying, okay, well, I know that this number is true, so what must the rate of the reaction be at this time interval? Well, we would say that rate equals delta H2 over delta T. H2 is a reactant in the reaction of H2 and I2, so it'd look like this. And so I'd say, well, okay, negative 0.067 over a 10-second interval would equal positive 0.0067 moles per liter per second. And so that's the number that we get here. So average rate or instantaneous rate, whichever one is helpful. We're going to typically be doing average rates just because we have the formula handy. and we don't want to deal with calculus. Oh, sorry, coughing, scratchy throat. I know, I like calculus too, but not everybody wants to do calculus, unfortunately. All right. How do you measure a rate? You're going to actually do this in the laboratory this week. The most common way of using a tool to measure rate... Oh, I'm going to cough again. Just a second. Sorry about that. The most common way to measure rate is to use some sort of spectroscopy. Particularly useful if your solution has some sort of color or quality that light can absorb in it. Then we can use a colorimeter. So a colorimeter lab is something that you've done like 7 or 8 times in this class. Not in this class, but in chemistry. Early on in the quarter, we worked with the colorimeter when we were using what was it, iron thiocyanate. The solution was orange, so you put it in the colorimeter and it gave you an absorbance. What we can do is we can say that the absorbance of a solution is equal to some constant times its concentration. And then we can plot absorbance versus time on a graph. And so basically what happens is you start a reaction, you put it in the cuvette, and it starts to do something like this. And because absorbance is proportional to concentration, you're effectively graphing concentration over time. Now, you could calibrate the detector to figure out what the concentration of this is, or you could just say, well, it's proportional by whatever epsilon is. So I don't particularly care about the concentrations. I just need to know the rate. And so you can do that. So this is actually what you're going to do on Friday. We're going to give you a very simple reaction. We're going to give you crystal violet, which is this like purple dye. And we're going to give you sodium hydroxide. And when you react the two, the result is a colorless solution. What you will get to do is you will get to explore the order of the reaction. We're going to talk about order in the lab. And then on Monday, when we come back to lecture, I'll talk about order again in the actual lecture content, because we're out of time for the day. But the gist is that you're going to be able to determine how does the reaction of crystal violet function. Does crystal violet and hydroxide react by one of each molecule bumping into each other? Or do I have crystal violet bump into another crystal violet, and then that reacts with hydroxide or something like that? Or does crystal violet have nothing to do with this, and it only depends on hydroxide? We're going to discuss more on what all of that means in the lab on Friday. Hopefully when my throat is less irritated. All right. Now, any type of spectroscopy that tells you how much stuff there is in your solution will also work. You can actually do this with NMR, believe it or not. If you have a 1 molar solution and you put it in the NMR and you know how tall that peak is, you could then do a reaction in a sealed tube and then take the NMR later and say, oh, well, it's half as high, so I've used half of my stuff up. So you can figure out a rate on how long it's been. I did a little bit of this in graduate school, where I'd take an NMR tube, I'd put it in a boiling oil bath, so I'd heat it like 180 degrees Celsius or whatever for like 16 hours. Then I would go rinse the tube off and then go put it in the NMR machine and see if there was a change, and there was. So you could say, oh, okay, I started with this much, I now have this much, It took 16 hours because I had a timer going. I can figure out the rate of the reaction over that time period. So when we come back, we're going to talk about... so this is just a little, like, blurb about... Like, oh, I can control stuff by, like, grinding it into a powder, or I can heat it, or whatever. But this is what we're going to be doing on Friday. And then we'll talk about that again on Monday. So, yeah, that's really all I got. So thanks for coming out to the lecture. Make sure that you are working on quiz number 16. Quiz number 16 is a lot harder than it appears. Maybe it's not super difficult, but it is tedious. When I wrote the key, it took me like an hour and a half, and I was like, oh man, this is obnoxious. Why did I make these problems so difficult? And they're not difficult. It's just that they're long. So please, please, please ask me questions if you have them. And the electrochemistry lab is also due on Friday. Make sure you ask me questions about that if you're stuck. Honestly, if you have to pick one to focus on, I would focus on the quiz. The electrochemistry lab, I'm more or less going to see that you got close, I guess we'll say. Yeah. All right. My throat's scratchy. I can't talk anymore. I'm going to call it a day here. Have a wonderful rest of your day, and we'll see you on Friday.